Hello and welcome to the second day of sixth week. So we have been discussing about the projection operators, and in the previous class we discussed about the complete projection operator and also introduced the incomplete projection operator. So incomplete projection operator is expressed in terms of the character of the representation. So incomplete projection operator is given by this particular expression. Okay, so how do you get this particular uh, form of projection operator, which is incomplete projection operator? So this is very easily it can be formulated. So let's try to do that first. So we had the complete projection operator. Okay, so this one was as written as the in terms of the symmetry elements, right? So what we got there is this, and sum over R for the matrix elements S prime T prime for a particular irreducible representation J over all the symmetry operations. So that was the complete symmetry projection operator, because it deals with all the matrix elements, right? And to start with, we also got when we went to the special case where we deal with only the diagonal elements. So we get this one as you take the diagonal elements as T prime, right? So that's what was our projection operator that we dealt with in the last class. So if you sum over both the sides over the element T prime, okay, so you get this is equal to, you can take this one out, so Lj by H, and then you sum it over T prime, and you already have a sum over R, and then you have the matrix elements, right? Now this metrical element and the symmetry operations, they have nothing to interfere with each other, so you can interchange the position, right? So you can swap the position. So what you have is, you can rewrite this as Lj by H and sum over R, and then you can write separately sum over T prime of this, okay, correct. Now what this is it corresponds to, the character of this jth irreducible representation, correct. So I rewrite this one as Lj by H sum over R, and this one is chi of R for the jth irreducible representation, followed by the symmetry operation. And this particular one we can write as P J simply, correct? Because this, you can see, this is nothing but the sum of all the projection operators, right. So, this Pj is the sum of all the projection operators individually that you can form, and the complete set will form a complete projection operator. So, this is my expression for the so called incomplete projection operator, right. So, that is what we wrote down here. So, now if whatever be the j, so right on your screen the j is assumed to be E, because in the last class we already discussed about the projection operator for irreducible representation E for C3b point group. Okay. So, it can be anything. So, now since we have looked at the effect of the complete projection operator on any given arbitrary function as xz plus yz plus z square, and we saw that ultimately with two projection operators, two different function comes out to be the basis of the representation E, and those were xz and yz. Now, here let us verify whether our this newly formed projection operator, which is known as incomplete projection operator, in terms of the characters of the particular ith or jth irreducible representation that we are concerned with, whether they give the same result or not. So, what we do, we now easily can form this particular projection operator. So, what you need to do, you need to have a character table of that particular point group with you, because you are going to use this character table. So, we are dealing with the representation E. So, you should know what are the characters for this particular representation for C3b point group, right. So, you find out a particular character table for this for this C3b point group, and now here you do the same thing here, that is you get the Li and Lj value that remains the same, and instead of multiplying the this effect of R on the function by the diagonal matrix element, here directly you are multiplying with the character corresponding to that particular symmetry operation. So, for identity you have and character 2, right, for C3b point group and the E representation. So, E, and then you operate identity on this function and you get back the same thing, and when you operate C3 you get the same result as we have seen in the previous example of complete projection operator, because the effect of R is not going to change, and then you multiply by the character of C3, which is -1, correct, because you will see that C3 and C3 squared, they are clubbed under the same class, so both of them have the same character. So, you do it for C3 squared and then you do it for the sigma v's, which has the characters to be equals to 0. So, 0 multiplying with all this ending up 0. So, when you simplify the whole thing, you get this, and even more when you simplify, ultimately you get this xz plus yz. Again, this is not surprising, because that projection operator Pj, which we are using right here also as Pe, that was formed by summing up the individual projection operator P11 and P22, right. So, we are getting the pretty much the same result, because xz and yz, so they are combined by this addition, right. So, which means that xz and yz, they together form the basis of the representation E. Now, you can see the difference also. The difference was that in the case of complete projection operator, each functions were separately pointed out. So, they turned out to be the individual basis for E representation, xz and then yz. But here you are not getting them separate, but you are getting them as a combined function xz plus yz, which is again is not too surprising, because here you are using only one operator. In the previous case you used two operators, p11 and p22. Here you use only pe, right? So one operator cannot give two functions, right? That's very well understood. So here we are getting one, but in essence that solves our purpose, because we know what are the component of this arbitrary function xz plus yz plus z square form the basis of the for the irreducible representation E of C3 point group. All right. So now let's get into the real business. That is, how do we use this projection operators, particularly to form the SALCs. So by now we know the actual use of the projection operator, right? We used some arbitrary function and all, but that must have by now given you a clear hint that what this projection operator can actually do in real chemistry. So this projection operator is used to determine the proper ways to combine atomic wave functions to on individual atoms in a molecule into molecular orbitals that correspond to particular molecular symmetry. Okay. So here you must be remembering that when we discussed about the relation between group theory and quantum mechanics, we said that the wave functions, which are the eigenfunctions of an operator, particularly Hamiltonian operator in that case, are the they can form the basis for the irreducible representation for the molecule and the particular point group to which it belongs to, right? So here when we talk about atomic wave function, this also should be valid. Moreover, it's not only the wave function but also the a proper linear combination of those wave function, atomic wave function, can also form the basis of the irreducible representation. Okay, so we can actually go on to form the symmetry adapted linear combination. Now we have a problem when we try to write down the symmetry adapted linear combinations, or in short SALCs, when particularly we deal with the molecule having equivalent atoms. Say for example, like in benzene, like you have all the carbon atoms which are equivalent, or in sulfur hexafluoride all the fluorine atoms are equivalent, or you take like MOCl8, that kind of complex, all the chlorine atoms are equivalent, or say PF5 where 3 fluorine atoms in the equatorial plane are equivalent and the 2 in the axial directions are equivalent. So in those cases we have some problem, because each of this atom and henceforth the atomic wave functions, they contribute to the symmetry adapted linear combination. So we will see how. So in order to form the SALCs, what do we need to know? So first thing is that we need to know the irreducible representation to which any given set of equivalent atomic orbitals will contribute. Correct? So for example, if you take a benzene, so all the carbon atoms, if we think about, and the wave function associated with the carbon atom, or in other words the atomic orbitals of each carbon atoms, so how they are going to contribute to the formation of the particular irreducible representation that we are concerned about. And second, the explicit form of the linear combination of atomic orbitals that satisfy the symmetry of the properties of each representation, and that we have already mentioned earlier, right? So the ultimate molecular symmetry that has to be satisfied by the linear combination of atomic orbitals that we are going to form. Okay. So it's comparatively easier to start with one-dimensional irreducible representations, And then as we move on, we will go to the complexities of 2-dimensional and 3-dimensional. It's not really complicated, but you know, 1-dimensional is a lot more easier, right? So what do we do when we try to find out the SALCs for any given molecule? Okay, so the first thing, obviously, you have to find out the molecular structure and its symmetry, meaning the point group of the particular molecule. So we will start with the construction of SALCs of in particularly this ethane molecule C2H4. Ethylene molecule, and we will particularly concentrate on the sigma bonds, meaning CH bonds, right? All right. So once we identify this point group, which here is D2H, which is very easy to find out, and after finding out this one, what we do? We take certain wave functions as basis functions. So we are considering CH bonds. Now, what basis we can choose? The answer is anything, right? That has to satisfy ultimately the symmetry conditions, and that must be within that particular molecule. So what we do here, we choose the 1s orbital for each hydrogen atom. So there are 4 hydrogen atoms, so I consider total 4 1s orbitals, and based on that we will form a representation for this particular point group D2H. So we will choose the coordinates, and these are the sigma bonds, and we will label them as sigma 1, sigma 2, sigma 3 and sigma 4, fine. And then we will ultimately use this coordinates as a bond vector, which are essentially sigma bonds, to form the basis for the for this representation of D2H point group. So ultimately you will get a representation. So you should be able to form this representation very easily. So I told you about the unshifted atom concept. So using that, you can form the representation very easily. So the number of basis function in my basis set is 4, and in D2H point group, what are the symmetry operations that I have? You have so D2H, right? So what you have is identity. You have C2X, C2Y, C2 Z. Okay, so the C2Z, if you take the as a molecular axis, so if you just draw the structure, so you are designing as the 1, 2, 3 and 4, and these are the all 1s orbitals. So you are talking about the sigma bonds here. So this plane, if I call this plane as my xy plane, then perpendicular to the z. So this is my C2z, and then C2y and C2x are perpendicular to that, and then you have I, right, and you have sigma h, you have this sigma d's, right. So you have one sigma plane here and one sigma plane here, correct. So you have sigma d, you can call one as say yz and another is xz. Okay, so sigma d xz, sigma d yz. All right. So altogether you have total 8 symmetry operations. Now you have to find out the representation, right? So if you think about all the effect of all these symmetry operations on this basis function, so basis functions are nothing but this 1s orbitals, right? So identity will not change anything, and if the basis function doesn't move upon the symmetry operation, each basis function will contribute 1 to the diagonal, right? Meaning 1 to the character. So here there are 4 basis functions, all of them are unshifted, will contribute total 4. Now if you think about C2x, so if this is my x and this is my y, so let me draw it somewhere else. So this is my x and this is my y and this is my z. Okay, so say this is x and this is y. So this one, what will make, 1 will come to 2, 2 will go to 1, and this one also. So none of these basis functions will survive. And what about this C2? So this will also, 4 will be interchanged with 1, 3 will be interchanged with 2. So none of them will survive. So there will be no contribution to the character. So both this and this will contribute 0 to the overall character. And C2Z, so that also it will rotate the molecule 180 degree about the z axis. So none of the basis functions will stay at their place. So that will also contribute 0. I will change everyone because 1 will come here, 3 will go here, and this one will come here and 2 will go here. So there is no unshifted atom, that will also contribute 0. Now sigma h is nothing but the sigma xy, correct? So 1s orbital is spherically symmetrical, right? So there is no separation of charge also. Therefore this plane will keep all the basis functions intact, meaning it will contribute 1 1 each, so together it will be 4. And then sigma dxz is doing the same thing as the C2 plane, C2x, C2y, and the other one is acting as C2x. So both of them will contribute 0. So this is my representation, right? So if I call this as gamma, and that's what my intention was. So the the representation gamma is like this, and you can see how easily I could find that out, right? I didn't have to form a matrix or anything. Directly I could find the representation based on the characters, and when you use this particular basis functions. So once you have found this gamma, then the next step you have to reduce this, reduce to the irreducible representation for that particular point group D2H. Okay, so in order to reduce that, you have to use the formula that we have already used. That is, if you have to find out how many times a particular ith irreducible representation will occur. So for this, in this case, see, all of them are written in a way that they form a class by themselves, right? So each one of them forms a class by itself. So there are total 8 operations, 8 classes, therefore 8 irreducible representation. All of them will be one dimensional. So here it will be 1 by 8 sum over r, and then the chi of this gamma, here we have named it as gamma for each r, fine, and then chi of the particular I for that particular operation. So use this formula and get the irreducible representation that is contained within the representation gamma that we formed. So if you solve using this equation of AI equals to this, then you will see that you can find out gamma to be equals to AG plus B1G plus B2U plus B3U, where this AG, B1G, B2U and B3U are the irreducible representation of belonging to the point group D2H. Okay, so in the next step, what you have to do, okay, so here it is not A2 prime, so this is P of AG, Okay. Uh, so we have taken this basis functions and the bond vector sigma 1, sigma 2, sigma 3, sigma 4. So you take any particular basis function out of your basis set. So I choose sigma 1, and then you form the projection operator for each one of those irreducible representations that you just got after reducing gamma, and then operate each of this projection operator on this particular basis function, which is sigma 1 in our case. So let's first operate PAG on sigma 1, and then after doing that, by now you know how to operate P. Here we are using incomplete projection operator in terms of the characters. So after doing that, we get this result. When I do the same thing for B1G, I get this result, and for B2U this, and for B3U this. Now you see what we are getting essentially. To start with this 4 basis functions, we are finding that this particular combination, that sigma 1 plus sigma 2, sigma 3, sigma 4, is forming a basis for AG. Okay, that not necessarily is forming a basis for any other thing. Similarly, for B1G, we are getting a particular combination of sigma 1 minus sigma 2 plus sigma 3 plus minus sigma 4 is forming a basis. And for B2U and B3U, using the particular projection operator operated on sigma 1, we are getting this 4 set of combinations of this atomic orbitals that we started with as basis functions are coming out to be the allowed combinations, symmetry allowed combinations that transform as the irreducible representation AG or B1G or B2U or B3U of the particular point group D2H. Okay, so in this way we can find out, and this each of these are called symmetry adapt linear combinations. So we started with 4 functions and we got 4 SALCs. Okay, so each one of them will transform as the respective irreducible representation. So I will suggest you to verify if this particular function, okay, say sigma 1 plus sigma 2 plus sigma 3 plus sigma 4 will form a basis of AG or not. Similarly, sigma 1 minus sigma 2 minus sigma 3 plus sigma 4, will it form a basis for B2U? It is very easy to do. You take this SALC that we got, operate all the symmetry operations, and just see what is the symmetry property of this combination, whether it is plus 1 or minus 1. Okay, and then you will get the characters, and then you match with the character table for which particular irreducible representation it belongs to, and you will see that yes, this will be correct. All right. Now one thing you notice here, when we form these SALCs, we really didn't care about that term Li by H or Lj by H. Okay. Because we are interested in the functional form, okay, how these sigmas are related. Okay, so the those coefficients that we left out can be easily found out by you while doing the normalization, and which is not so important stuff, but to know which are the particular atomic orbitals that can combine, and in which way they can combine, which particular way they can combine, so that they can adapt to the symmetry of the final molecule. In our case, this hydrogen 1s orbitals, they are combining with the carbon to form the basis of one of the irreducible representation of the D2H point group, to which the final molecule C2H4 belongs to. Okay, so this is how we form the symmetry adapted linear combination. So you can verify for other type of bonds, and you can go to higher order of representation, that is to 2-dimensional or 3-dimensional representations. So we will take those representation in the next class, and we will also try to look at the the energy contributions in case of like formation of the molecular orbitals and so on. So we will try to look at the Huckel's approximation and beyond. So till then, I thank you for your attention and see you in the next class.